Okay, we are back for a proof of the inclusion-exclusion principle, which hopefully just flows naturally from what we were talking about earlier. What is the inclusion-exclusion principle? Well, in the most general form, it says that you have n sets, and you wish to compute the size of the union of all of those n sets. So we call the sets A1, A2, A3, all the way up to An, and the principle says that if you take the union of all of them and take the size of it, then it's the same as, well, the intuitive explanation is that you first take all the elements in A1, all the elements in A2, all the elements in A3, etc. And that's what's happening here in this first step. We're summing from I equals 1 to n for the size of the ith set. Of course, that vastly overcounts things, and so you count every object, and then you subtract out as a correction all of the pairs of sets. So you take this notation saying, let I and j be let I and j be numbers between 1 and n, and so take the intersection of ai and aj for all possible combinations I and j. Now, by insisting that j be greater than I, this is just a very technical thing, then that's a way of ensuring that we are only taking the intersection of like A2 and A3, not also A3 and A2. That would be kind of dumb. So any pair of sets AI, AJ where one of the indices is larger, so that's just all the pairs of sets. And take every pair of sets and take their intersection and take the size of that intersection and subtract out by that. So you're subtracting all of the pairwise overlaps. And then you add back in all of the triple-wise overlaps. So now consider any three numbers, I, j, and k, which are between 1 and n, once again insisting that k be bigger than j, which is in turn bigger than I. And so these three sets are all well, they're three different sets, and also that you're not overcounting the number of triples. And now you add those back in. And then you just keep on doing that forever until n times. You do this sort of correct, you sort of do initial, then you correct, then you fix the overcorrection, and then you keep going until the final one, which will be positive or negative depending on whether n is even or odd. If n is odd, the last one will be negative. No, the last one will be positive. If n is even, the last one will be negative. Yeah, so I guess I could even add in here if I really wanted to. This is just going to be -1 to the, what did I just say? If n is odd, the last one will be positive. So it's like n plus 1. Okay, great. We could stop here, or we could try to give an argument for why this is true in the most general case. Well, okay, so here's what we do. It's a counting argument ultimately. We want to say that that this method sort of counts correctly every object in this set. So what we now need to do is sort of to simultaneously consider every possible object in this union, judged by how many intersections it appears in. Okay, so let's take an arbitrary element from the set, hopefully this argument makes sense, A1, A2, all the way up to AN. And what I want to show is that for this arbitrary object, this is this right-hand side correctly counts this object. Well, of course, this object appears just once in this set on the left, and so we should hope that by following this method on the right-hand side, that this object x is accounted for just once. Okay, let's go. So now, suppose that x appears in precisely k of the n sets. Okay, so that just for example, if k is 5, then this element x is in the intersection of 5 of those sets. And if k is just in like A2, for example, and not in any of the others, then k would be 1. Okay, well, now we just sort of track how many times x is being counted on the right-hand side. Well, if x appears in precisely k of the n sets, then in the first step, x gets counted k times. So that's what I'll just write down. So we get k choose 1. We have just counted x k choose 1 times. But then, if k appears in precisely k of the n sets, here we're taking every possible pair of sets. Okay, so now we have to say to ourselves, all right, if x appears in k of these sets, and we are now taking every possible pair of sets, well then, how many times does k get counted? Well, there are, if x is in 5 sets, and every time it's in, so how many times is it in the intersection of 2 sets? Well, that boils down to, in the 5 sets that x lives in, how many pairs of sets is it in? And the answer to that is k choose 2. So what is k choose 2? It's the number of ways given the k. I think I might have said 5 a second ago, or in my brain I was saying 5. But what I've really assumed is that x appears in precisely k of the sets. So if x is in k of these sets, then k choose 2 is just the number of ways of choosing a pair of sets from those 5 sets. And so essentially there are k choose 2 pairs of sets that x is in. And thus over here, when I construct every possible pair of sets, take their intersection and take the size of that intersection, well then, how many times have I counted x in that computation? Well, x is going to contribute, so to speak, to this second term. X is going to contribute to that second term based on how many pairs of sets that x is in, and x is in k choose 2 pairs of sets because x is in k sets. All right, this is not the perfect explanation. I feel like it could be slightly better, but okay, whatever. What happens in the next step? Well, now I form every triple of sets, and I take their intersection, and I take the size of that intersection, and I add up all those numbers. And so how is x being accounted for in this process? Well, now I have to sort of ask, well, okay, how many times does x's presence in get accounted for over here in this step? Well, x is in precisely k of these sets, and so there are therefore k choose 3 ways of picking 3 sets that x is in. And so if there are k choose 3 ways of picking a triple of sets that k is in, then x is being counted k choose 3 times in this step. And so that's being added. Okay, so I think you see how this goes, right? Then in the next step, x is in k sets, so there are k choose 4 ways of picking which 4 sets that x is in. K choose 4 ways of picking 4 sets that x is in, and that number is getting subtracted, and then we just keep on going until we get to the final one, which is how many ways are there for this to be true? Well, it's going to be k choose k, and that is to say, Oh no, it's not to the final one. We don't go all the way to the final one. We stop when we get to k. There are not n terms in this. There are k terms. Because since x is in only k of the sets, then we keep going until we've counted every. Okay, so it's like a pair of sets, every triple of sets, and every set of size, every collection of size k of sets. And so the final subtraction or addition will be the number of ways. If k is 5, for example, then will be the number of collections of size 5. But x, by assumption, is in k of those sets, so it's just k. Okay, well, what do we have here? So what sort of is this? When we take all of the ways given this is, remember, we're counting x. There are k choose 1 ways or they're just k times that x gets counted. Then we subtract by k choose 2 because there are k choose 2 pairs of sets that x appears in. We add k choose 3 because there are k choose 3 triples of sets that x appears in, etc. Why does this correctly count x? Well, now we just note that by our previous theorem, the previous theorem says, the one that we just spent 20 minutes reviewing, previous theorem, is that in fact k choose 0 how did we do that? Yeah. Minus k choose 1 plus k choose 2. This was the previous theorem, all the way up to minus or whatever to k choose k. That this is 0. In other words, the number of even-sized subsets is equal to the number of odd-sized subsets. Well, here the only thing missing is k choose 0. Yeah. This just is k choose 0. Why is that? Well, I guess maybe the simplest way to well, it just is, right? Subtract k choose 0 from both sides, and now you get this precise thing. Or maybe well, so this was the previous theorem. I guess if we're really going to do this all out, if anyone is still watching, then you could take the previous theorem and just move things over, right? K choose 0 is just k choose 1 minus k choose 2 plus k choose 3 minus and all the way up until we get to k choose k. And therefore, the grand conclusion of all of this is that this entire right-hand side is just 1. Or it's not that the entire right-hand side is 1. It's that for this arbitrarily chosen x value, which is in precisely k of those sets, then it gets counted once. That there's some sort of counting, there's some sort of overcounting, undercounting, correction. But based on our analysis, for any particular object, the right-hand side does in fact count it the correct number of times, which is 1 time. And if every single object gets counted 1 time, based on, we're sort of doing a proof by cases on how many of the n sets x appears. So we said arbitrarily that suppose x appears in k of the n sets. So no matter how many of the sets x appears in, for each k, we have argued in general that x gets correctly counted, which is to say it gets counted once. Okay, worst ever lesson on the inclusion-exclusion principle. It only took an hour. Goodbye.